Started. Thank you, Chris. I'll let Jens get started setting up here. So it's my great pleasure to introduce Jens Kolbe. He is our second early career spotlight speaker. He earned his PhD from TU Darmstadt with a thesis entitled Learning Motor Skills from Algorithms to Robot Experiments, which was recognized via the George Garreau Award as the best robotics PhD thesis in Europe in 2012, so 10 years ago. Since then, Jens has become an associate professor at TU Delft, and he's been recognized as an Ellis Scholar. His group studies many aspects of machine learning with applications to robotics, including learning skills, motor primitives, RL, imitation learning. And the last thing I'll say is that Jens has made significant service contributions to the community. For the last 5 years, he co-chaired the IEEE RAS Technical Committee on Machine Learning. He was program chair for CARL in 2020, and he was the RSS Virtual Conference Arrangement Chair in 2020 when we were all scratching our heads wondering what was going to happen. So he's going to tell us about using interactions to teach robots. Please join me in welcoming Jens.
Thanks a lot for the very kind introduction. Let's start with something a bit more fun. Who of you can flip pancakes in the air? 1, 2, 5, 10? Not many. OK. Then robots surpassed the rest of you about 12 years ago. I guess many of you have seen this video by Peter Komuchev, went viral back then, using a combination of imitation learning, so giving a demonstration and the robot trying to mimic that, and reinforcement learning to fine-tune that movement. And personally, why I like that is because for the reinforcement learning part, they used an algorithm I developed. It takes about 50 trials or so until it can do it, which is pretty impressive. But there are obviously also quite a few limitations. It's effectively an open-loop movement, needs a good demonstration, and so forth. So I'm still pretty confident that I myself, once I get around to try to learn that skill, will be able to do it more quickly. Let me start with giving a brief overview of how people learn. It's not going to be scientific in any way, but I still think it's very interesting to see how that connects to things we do in robot learning. We already saw using a combination of what happened now. Nope. Yes. Okay. I'm really sorry about that. Okay. Okay. It's not a video.
It's not?
Nope.
When you get to the presentation, you blink
Yeah.
take it off.
And that doesn't allow me to duplicate. It works for a second and then fingers crossed.
Do you want to skip to the next slide to see if it's...
mine.
It's always the same slide, right? Is there some
Yeah.
animation on it?
Nope. Okay, let's see. So on the previous slide, I had a combination of imitation and reinforcement learning like we saw in the pancake example. One of the other things you can notice if you think about how humans learn is that while we're young and a baby, it takes quite a long time until we learn basic things like grasping and walking. But once we have those basic skills down, then we can actually very quickly learn related skills, like grasping a book in this example. If you translate that to robot learning, that might be doing some higher level planning with a fixed skill library, or some form of transfer learning or meta learning. The other thing is we as humans have a pretty good understanding of our environment and how that works. So we have an understanding of intuitive physics that an apple is always going to drop. And we can use that to do mental rehearsal, to just think about what we should do in order to achieve a certain task and how the environment is going to change before we actually try it out in the real world. So that's then connected to model-based learning and planning and optimization, or also sim to real, for instance. What I want to focus on today is interactions with teachers. If you think about how you, for instance, learn a new sport, you're not going to get an initial demonstration and a rough description of what you're supposed to achieve, but rather you're going to have a coach look at what you're doing once in a while, then give you some corrections, some feedback, some hints to get you unstuck if you went down a wrong path, or maybe just to tell you on what you should focus next. Henny already talked a bit about interactive learning yesterday, but you started from the assumption that it's actually useful and really helpful to make robots learn quickly, and then you went on to discuss that from a human-robot interaction point of view. But if I talk to some people, not all of you seem to be convinced yet that getting a human involved really in the learning loop is a good thing to do. And my goal today is to try to convince a few more of you. So, teaching through interactions. That means that we're going to have continued student-teacher interactions while the robot is in the process of learning. So you could provide some additional demonstrations, some other form of intermittent feedback. And you see that more and more in robot learning. I believe there are huge benefits to that in order to speed up the learning process, which in turn enables the robots to learn more complex tasks. And hopefully, if we get the HRI side down, is also intuitive for humans, especially if they're non-robotics experts. And the cool thing is, I now talked about how humans learn. Also, if we look at how we teach other agents, like animals, that's one of the things you constantly see. So to start out, I'm going to talk a bit about interactive reinforcement learning. I'm going to give you another example, ball in a cup. The goal is to catch the ball in the cup. That's my cousin's daughter. She was around 10 years old back then and took her 35 times to catch the ball in the cup. If we do the same thing like we saw in the beginning with a robot, start with a demonstration, you try to execute that on a robot, works kind of, but misses by a few centimeters. After 15 trials, it's already quite a bit closer. Now it's trying to optimize the distance between the ball and the cup. It takes about 40 trials to sometimes get it in, usually it bounces off, and after 100 trials, it has converged. So that didn't have any interactions yet, except that Katharina had to practice quite a bit to get the demonstration down, and also I had to learn quite a bit about how to design the reward function, so we had some iterations in the learning process there. So why not formalize that a bit? So, interactive learning. Before I show you how ball in a cup with interactive learning looks like, I'm just going to give a brief introduction about the setting. So we have an agent, a robot, and an environment. We have a state, and then the robot needs to decide which action to take next, so that's a policy. And then that looks very familiar, like a reinforcement learning loop or just a generic controller. Now what we have additionally is a teacher here in the center who is able to observe both the states and the actions the robot is taking, and then once in a while he or she is going to provide some kind of feedback. We heard in Henny's talk yesterday there's quite a spectrum of kinds of feedback you can give, And I think there's a big trade-off between how easy it is for humans to provide feedback and how informative that is for the robot. So on the one end of the spectrum, you could have really a binary feedback, works, doesn't work, which is really easy for a person, but not very informative for a robot. On the other end of the spectrum, maybe you have a complete demonstration, which helps the robot a lot, but can be very tricky for a human demonstrating, because then you really need to learn how to use the system to demonstrate it. So in practice, what my group figured out that works really well is to do something in the middle. So we settled on using corrections, mainly in the action level. So that means you don't need to give the robot the correct action to take, but rather you tell it a relative correction. You should move more in that direction, for instance. That seems to be a nice trade-off between how having something that's still doable and still informative. To give you an example of an interactive imitation learning approach, here's COACH. It stands for Corrective Advice Communicated by Humans. It's a bit confusing. There's another algorithm that is exactly the same acronym that also does something kind of similar. Anyhow, so what the setting is, the car, or the robot in this case, is supposed to drive from top to bottom. It has some initial policy, and then the human teacher is once in a while going to jump in when the robot is screwing up to give corrective advice, move more to the right, move more to the left. What's also important to note is that this is truly interactive, so the robot is going to directly adapt and take the correction into account. And then once you've done that, once, hopefully the robot has learned from the corrections and is able to do it a bit better, so the human teacher needs to jump in less frequently. And then in the end, hopefully the robot is able to do it on its own. So now we could say, okay, I have a nice interactive imitation learning approach. We could just replace the initial demonstration where Katharina had to practice so hard by this interactive learning approach. And then we, again, use reinforcement learning, or in this case, policy search, to fine-tune it. But I think we can do better by really doing it simultaneously, all in one. So how we did it there is that we actually modeled the human input as a form of exploration. In reinforcement learning, you need exploration, so the robot needs to try out new things in order to figure out what works better and what works worse. And that's usually a form of perturbation or noise on top of the nominal policy. And now we additionally treat the human corrections as a form of exploration. And that works very well if the algorithm can cope with off-policy data. Standard policy search looks something like that. So need to explore and do a number of rollouts, so try out different strategies with a bit of exploration, and then you evaluate how well that worked. Here it's just an episodic setting, and then you apply your favorite policy search approach to update the policy parameters. What changes now if we make that interactive is that we additionally get the human in here. Why do we have this hard switch? Turns out that if a human is trying to demonstrate something and the robot is additionally also exploring on its own, that gets very confusing. And here we indeed used COACH, the algorithm I introduced a few seconds ago, for the human guidance. Then that looks like that. Now we can not see anything. Huh. Okay, let me try once more to duplicate. No. Okay. So, let's try to play that once more. So we can start from scratch. But additionally, instead of the demonstration, now we have a teacher sitting in front of the robot providing corrections like move more to the right, move more to the left. And then within 20 trials or so, the robot can catch the ball in the cup. As a plot, that looks something like that, where you have the number of times the robot tried here on this axis. Here we have a cost, so lower is better. The blue and green are the interactive approaches, and in red is a reinforcement learning approach without any interactions. So for both the interactive approaches, it took about 20 trials to get it in. For the reinforcement learning, it takes about 200, so an order of magnitude longer. And then the main difference between the green line, which is imitation learning only, and the combined imitation learning and reinforcement learning is that You can get pretty good, but only by having the robot fine-tuned, you can really get the best final performance. So I think that's very interesting because it nicely shows that the strengths and weaknesses of a robot and a human are very complementary. A human is very good at giving the rough idea and the rough demonstration, figure out the big strategy, while people typically are not good at fine-tuning and being reproducible and very accurate. And that's something a robot excels in. So let's switch gears a bit and talk about interactive imitation learning. And actually, I'm also switching gears once more and talking about slightly higher level learning. In imitation learning, the thing you want to do is not just replay what you've seen. That would be boring. You want to generalize to a new situation. So for instance, you should be able to grasp a cup no matter where it is placed. In this example, we additionally have a coaster. So the robot is then supposed to figure out with respect to which objects it's supposed to move or relative to the world. As long as the cup and the coaster are always together, that doesn't make a big difference. And if you forget to demonstrate that maybe those two objects can get separated, then once you have the two examples on the side, then the robot suddenly is lost because it's ambiguous. And you would either need to go back and collect more demonstrations, or what I'm going to show you next is actually have the robot ask for feedback and try to get the human teacher to disambiguate that for it. And what's really interesting also is that in many situations, it doesn't really matter. Even if there's an ambiguous situation, if the action the robot would take is effectively the same thing, then there's no need to bother the human with a question. So our approach is only going to ask the human teacher to disambiguate if that's really crucial for the robot to complete the task. So here we taught the robot how to put a cucumber into a crate. It can do it from different initial positions of the cucumber. But what we forgot to teach it intentionally is what happens if you swap the position of the two crates. So now it doesn't know whether it should move relative to the world coordinates or relative to the position of the crate. So it can still do the first part of the movement. Now it gets stuck, and it stops. So we need to give it a little correction, a little feedback, so it can disambiguate that, and from now on, it knows that. We also ran a user study for that, where we compared kinesthetic demonstrations and teaching, where you're supposed to collect quite a few demonstrations that are sufficient to disambiguate all the things the robot might encounter. So there you need a few corrections. You can try it out. You need to figure out, OK, I forgot something. I collect a few more demonstrations, and hopefully it works in the end. And we compared that to LIRA, which stands for Learning Interactively to Resolve Ambiguities, which is exactly this interactive framework where the robot is asking if it needs to disambiguate something. So there, we just saw one additional correction. Then if we compare them, KT, a bit more on the left, is the kinesthetic demonstrations, and LIRA, the interactive one. And for all of those blocks, lower is better. So both in terms of demands on the user and in terms of what they prefer to do, the interactive approach does a lot better. So far, I've only shown you things that don't involve any deep learning. But there's no reason why not to do that. So we can also apply these ideas if we want to learn directly how to control from images. Well, not entirely directly. You still need to bring it down to a manageable size, some latent representation as usual. So one idea could be to start out collecting a few bit of data of your environment, maybe not exactly the task you're interested in, and then train an autoencoder. Then use the encoder and attach a policy head on top of that. That works. It's quite a bit of additional work, and depending on the data you collect, it might not work that great. So instead, again, can't we do that at the same time? And indeed we can. So now the main objective is to learn a policy, and as an auxiliary criterion, we have the autoencoder, so the reconstruction of the input. And then to come back to the little driving example, here you have Ducky Town environment where the robot driving around. On the top here, that's the camera image, and that's the reconstruction from the latent state. And then it takes around 9 laps or so, and then you can also intermittently test how well the robot does. You just don't give it any feedback any longer, and then you can see that it already does quite well. That works very well if you can directly map from states to actions, but for many tasks you actually need some form of memory, either because you need to remember something or simply because you might want to have an estimate of a velocity of some objects. So the most natural thing to do is to include some memory in the network structure. Either you stack a few images or you include a recurrent structure like an LSTM in this example. And the other thing that changes is now we are not trying to reconstruct the observation directly, but the next one in the future. And if you're collecting data, that's easy to do. That actually then forces the network to learn about the dynamics and the memory because it needs to predict into the future. So here's an example of that. The goal is to collect these fake oranges. To make it a bit more tricky, the robot can only see the part here in white. So it needs to memorize where the objects are so it can touch them later on. And here, that's what the network sees here, and there, again, the reconstructions on the bottom. And then already after 15 minutes, it does quite well. Here we're using keyboard interactions to provide the corrections. And then after 35 minutes or so, it has reached peak performance. And what's really cool is if we have a good policy already and a good representation, we can actually transfer it to a new task and very quickly adapt it to that. So here now we're covering up the oranges with pairs, and it's supposed to avoid those. Here you can really see the corrections we're providing, and then after 3 minutes, it can already do it. And then if you train a bit more, like after 10 minutes, it has converged. The things I showed you so far were in action space, corrections in actions, which is nice because it's direct. However, if you have a robot like that, it also gets high dimensional and can be very non-intuitive. So why not teach in state space instead, so in end effector space? That needs an inverse model to map back to the actions you actually want to do on the robot. If you just buy it and you're interested in the end effector, that's something you get from the manufacturer. But in some other cases, like for example here, you might not know this transformation, so this inverse model. So here the task is to use the laser pointer to track the shape on the whiteboard, and we want to give the corrections directly in the space on the whiteboard. So here within 20 minutes or so, the robot learns to both do the task of tracking in the letters and also learns the inverse model it needs in order to map from the state space to the actions. Then one final block, going beyond kinematic trajectories. If you're interacting with the environment, you also have forces that you want to exert and have complex contact dynamics. So here, for a very classical whiteboard wiping task, with this kind of robot, if you don't have a force torque sensor, you can't actually record the forces. So what you're going to see now is Anna providing a correction, so effectively pushing the robot down, which is going to put the attractor below the whiteboard and also to increase the stiffness in that direction. And then with just one little correction, it can learn that, and now you're going to see a validation that actually learned to do that. What we learn here is attractor fields represented as Gaussian processes, both for the stiffness and the trajectory. You see the original trajectory in red, the final trajectory in black, and the background tells you how much force it applies. One final example, trying to restock in a supermarket. If you would do that in a very traditional way, do a pick and place action, you go to the object, stop, close the gripper, and then continue moving, which is very slow. If we want to, here we want to do it in one nice fluid movement, but then you actually get interesting contact dynamics and it can bounce off. And the additional difficulty is that the timing of the gripper is very imprecise, so we needed to teach it a trajectory that is robust to that. We started out with a pretty slow demonstration. If you've ever tried that, it's really hard to give good demonstrations if you want to move quickly. And the goal was to speed it up 4 times, so bring it down to 5 seconds. And that's what you're going to see here. It can do that in one nice fluid movement in 5 seconds. And here we gave the users the opportunity to separately tell the robot where it should speed up and how to correct the trajectory. And then what we learn can generalize to different initial positions of the object. You can also mess with it a bit by moving the object around. However, also here, it's unaware of what it knows and what it doesn't know. So if the object is too far away from what it has seen, it's just going to stop and wait until the object is close again, or you provide additional corrective feedback. So to sum up, I talked a lot about teaching through interactions. And I hope I could convince you that this is a promising way of speeding up robot learning. Because humans and robots have very complementary strengths and weaknesses. And it's not a standalone thing. You can combine it with many of the other ideas that people are exploring to speed up robot learning. The other side of the medal is, how do humans actually like to teach? How can we make it easy for people to teach? And for that, Hini's talk was great yesterday. So I fully agree with the statement that assuming humans are oracles for training data is a bad idea. In all the things we tried, that never was the case. However, to paraphrase the famous sentence by George Box, all models are wrong, but some are useful. I'd say, at least so far, all humans have been wrong, but most have been useful if they're trying to teach a robot a new skill. So to sum up my talk in 2 images, I believe that it's a great idea to help robots to learn new tasks quickly by interacting with them while they're actually trying to achieve the task, in order to enable them to learn very quickly and efficiently, such that they can support us later on. So I'd like to thank all the people that contributed to the work I was presenting today. They put in countless hours of hard work. And I'd also like to thank the organizations that funded this research. Thanks a lot.
Thank you, Jens. So do we have any questions? I see a few people coming up. Okay, good. Excellent. Shall we start on that side?
Yeah. Thank you for the great talk. So I just have a question. In the cases you showcased, how robust it is for the robots against like adversarial interactions from human actions. For example, imagine you have a teacher who is like always giving the wrong instructions, or like sometimes give the wrong instructions. How would that affect the system's performance? Thank you.
Yes, excellent question. I'm going to answer in 2 parts. For the imitation learning part, we essentially assume that whatever the teacher shows is what the robot is supposed to learn. There might be some noise on that, but on average, that's what the robot is supposed to learn. So there, that doesn't really apply. However, where that gets really, really important is in the reinforcement learning setting. Especially, so very simply, if the reward of the robot and what the human is trying to teach doesn't align, or if the human is trying to be adversarial, then it's just going to fight it and it's not going to converge to anything. So one way to deal with that is actually think about interactive inverse reinforcement learning and trying to first figure out what the human is trying to achieve by learning a optimization criteria and reward function. And there's also quite a bit of work on that.
Thank you.
Hi, thank you for the talk. So my question concerns how do you solve, or is there a problem, and how do you solve a problem of correspondence between the human's feedback and feedback that is useful for changing the robot's policy? I'm imagining the case where you have some sort of deep network representing your policy, where the easiest feedback might be, change the weights in this direction, but a human can't give that feedback. The human has to say, move more left, move more right. How do you solve that mismatch, and are there best practices for designing policies that are more interpretable and more open to that sort of feedback that's more easily given by humans?
Yes, indeed. I don't have a recipe yet. And I think it needs to come from at least 2 sides. We need to think about it from the robot's perspective, about what's useful for the robots, and I could also think along the lines of going more the direction of active learning, that a robot is actually actively requesting information, but then you need to be careful not to totally overburden the human. And then you also need to look from the other side about what can people do, what do they prefer to do. Actually, it turns out that there's also a big difference between people and groups of people, how they like to teach the robots. I'm sorry, I don't have any answers yet. We now started working also together with people looking at it from the human-robot interaction perspective, so maybe in a year or so we can tell you more.
All right, thank you.
Go ahead.
Hi, great talk and a very impressive demo. And one question I have is, have you ever considered the case when the human's not an expert at giving these kind of feedback? Because it seems that PhD students obviously know how to work with the robots, but if you actually deploy this robot at a, I don't know, nursing home or someone's home, the person that's trying to use the robot may not be very good at giving feedback. I mean, in these cases, how do you still ensure that robots are able to learn from human feedback?
Yes. So we don't necessarily assume that a human is an expert. A human needs to know how to roughly solve the task. And quite often, it's actually an interaction of the teacher trying out to teach the robot something, then seeing, okay, it doesn't really work how I imagined it, and then changing the strategy a little bit. More practically speaking, yes, we are the university, so most of the people we had in the experiments are students. Quite a few have a computer science background, not necessarily robotics background. We tried to get in a few people also that didn't have any experience with the robots at all. Yes, you can see a big difference. And people that are playing computer games are amazingly good at teaching robots. But also the others managed.
Great, thank you.
So I do see there's some more questions, but I'm afraid we're going to have to stop them there. You'll have to ambush Jens.
Yes, I am around till Friday evening, so try to find me.
Great. So we're going to move directly then into session 8, the next session of short talks. Let's thank Jens again.
All right, thank you. The chair of the next session is Abdeslam Bouliaris.